We are going to be talking about pump controls and the different system components that are in there and how we can work with these systems. This is very important to us when it comes to being able to safely work with electrical systems. Because if you have to work with an existing piece of infrastructure, we need to be able to safely open and safely know how to identify what's in there. So we're going to be working on recognizing typical pump controls and components. The primary reasons for control systems is going to be the ability to use logic. Logic is very important because it allows you to design systems that are going to be safe. It's also going to allow the systems to be operated based on the situation, based on environmental inputs, such as is a tank full? Is the person ready for the pump to operate? It also allows the motor to be operated from a safe distance. Some of these pumps are operating on very high voltages, and you don't want to be a couple of millimeters away from a switch that's stopping 480 volts at 60 amps. That can be dangerous. So control systems allow us to operate the pump from outside of the electrical enclosure. Also, pumps tend to require high power switches that are very expensive. But if we use control systems, we can use very low power, low cost components to control only a few of the high power systems. So all your logic can be built into the inexpensive pieces that are controlling the few expensive pieces. So if we're going to talk about motor controls, the heart of any control system is going to be the contactor. The contactor is nothing fancy. All it is a switch. There's not much difference between this and the light switch on your wall. The difference, though, is twofold. One, this is designed for high power applications. Your light switch at home is not. And also, the light switch in your home, you need to actuate it using your hand. You need to physically go to it and actuate it physically. Now, for a contactor, it is not actuated physically, but it's actuated electrically. So if we take a look at the screen here, we have a very basic schematic of a control system. There's essentially three sides to this control system, or this contactor. We have the incoming power from our power source. We have our control circuit, which is controlling and actuating the contactor. Again, the contactor is just a series of switches. And then we have our output power, okay? Now, we're not going to get into the details of three-phase power, but if you're not familiar with three-phase power is what most large electric motors require to operate. And for this discussion, just realize they need 3 wires, where a regular single-phase or biphase pump only require 2. So that's why we have 3 wires running down to this pump, and each wire has a switch on it, has the contactor. Okay, so these are nothing fancy. They're just switches that are controlled by the contactor. So if we were to look at this, we have, on the control circuit, we have coils. These coils, when they're energized, when we allow electrons to flow around through them, it creates a magnetic field, kind of like a solenoid, and it's going to push these contacts into the closed position. When we have electricity flowing around here, these contacts are going to be in the closed position, and that's going to allow our electrical power to flow through our wires to our pump. But now let's say that we no longer have electrical power flowing through our coil. That means it's de-energized. That means that these contacts are going to be in the open position. So electricity cannot flow and get to the motor. So it's in the off position, the open position, open like a switch. Now, all control systems have these three sides: incoming power, control, and your load, your pump. Do you recognize this? This is a quick sketch of the CU200. And in this, we can see that we have incoming power, we have control circuit, and we also have our load, our pump. So even a CU200, which is what we use every day in the field, has these three sides. And when we're talking about diagnostics and troubleshooting, it's very beneficial to compartmentalize these sections. Think about, is the control system working? Is the input power working? Is the load working? A CU200 isn't going to look like the rest of these examples that we're doing because it's what's considered a printed circuit board, a PCB. And those just tend to be a little bit more complicated for someone that didn't design it to look at it and understand exactly what it is and what's going on. Now, this is our simple contactor with control circuit. Just to go through this one more time, if we have a battery right here, that's a symbol for a battery. So, right now, we don't have any electricity flowing in our coil. Our coil is de-energized because as electricity comes over here, our push button doesn't allow the coil to be energized. The push button is open. But if we were to push in our run button, electricity is able to flow through there, down and around, energizing our coil, coming to our battery, getting pushed around again and again and again. That energizes our coil, which pushes these contacts into the closed position. When those are in the closed position, that allows power to flow from our AC source, could be DC source, and into our pump. Okay? But now I want to make a slight modification that is going to make this system a little more realistic to what we typically see in the field. See this battery that we have right there? I don't want to install a battery. That's an extra component that we have to take care of. We have to charge that. Let's not do that. I would rather power, when I need to energize this coil, let's energize the coil off of the AC power that we already have. Okay? So now let's walk through this. We no longer have a battery over here, right? What have we done? Instead, we've energized our system through the AC power that's already coming in. So let's talk through this again. We have AC power coming in, coming up to here, but we can't flow through that point because our run button is not engaged. It's not in the closed position. So if we push that button in, suddenly electricity can flow. It's going to energize our coil and keep doing that as long as that button is closed. It's pushed in. Now when that coil is energized, that produces a force on our contactor, and that's going to close the switch. That makes sense? So this pump is going to run if our coil is energized. But most systems, you don't want to have to stand there with the switch to turn it on and off. We want to build some type of protections or automation into the circuit, into the control circuit. So we have the same system set up, but the difference is we have installed this float switch right here. So let's follow the electrons through here. We got AC power coming in here. It's going to come up here. It's going to stop here until our run button is closed. Then it's able to flow through here. But now it's going to go out to your float switch. And now the float switch gets to determine, does the coil energize or not, depending upon the position of your float switch. It could be in the open position, in which case electricity doesn't make it any further. So we would have to move this float switch into the down position, and electricity flows. Energizes our coil, and it's going to keep doing that until one of two things happen. Either the run button gets opened, we release it, or that float switch moves back into the open position. If either one of those switches open, our flow of electricity is going to stop. And in order to restart it, we will need both the run button and the float switch to be in the correct position. Now, if we were to talk about that, what we're doing is a logical and statement. We're saying, for the pump to run, I want the push button to be activated and the float switch to be activated. All right? Now, while we're thinking about that, I want you to ask the question, this run button and the float switch, are they wired in series or in parallel with each other? Does that mean, are they in different branches or are they the same branch? Well, let's follow the flow of electricity coming through. It comes through there. There's no branches between those two items. So that means they are in parallel. So if you want to build a logical and statement into your pump controls, we're going to use series configuration. Now, let's get a little more complicated. Let's say we have a system, we want the run button, we want the float switch, but there could be a situation where just because your tank is full, or maybe it's empty, depending upon what float switch you're using, you want to ignore the float switch and you still want to be able to operate your pump. Well, to do that, we're going to install an override button. We're going to install an override button just like this. Now, this override button is in parallel with the float switch because this is one branch and this is another branch. There's choices in flow paths. So in this situation, the pump's not going to run if this push button is in the open position. Flow doesn't flow through it because we're going to have electricity come in through here and it stops. It never reaches the coil. It doesn't matter what's going on with the float switch or the override switch. The run button governs. But now, let's say we push in the run button and we're flowing through here. Float switch is good, so we flow through here, we energize it. But let's say that's not the case. Let's say that the float switch is in the open position, not allowing electricity to flow. That's closed. It's going to come up here, but it doesn't go anywhere because it's open. But what can happen is if we push in our manual override, the flow of electricity is going to go around the float switch through the override and energize the coil. Got it? So what we're seeing here is a logical OR. We want to run the pump if the float switch says run the pump or if the manual override says that we should run the pump. But this configuration right here is in parallel. So parallel builds logical OR statements. But let's say we want to get even more complicated because we're not confused enough yet, all right? So let's say we're working in a context where the national power grid or the generator, whatever it is we're working off of, occasionally produces dirty power. We know the grid is supposed to be 240 volts, but we check it, and occasionally at different points in time of the day, we're only seeing 180 volts coming in. And you say, man, if I operate my pump at 180 volts, I'm going to burn it out. So I need to somehow protect my pump against that. Well, what we can do is install some type of voltage monitor. All right, what's going on here is this voltage monitor is connected to the incoming power, the incoming voltage, and it's measuring it. It's basically a multimeter that's measuring that voltage. See, it's in parallel, just like you would measure the voltage using a multimeter. And then there's some internal logic to this piece that determines if electricity gets to pass through it or not. I want to blow that area up a little bit and take a look at that. These types of components are called relays. Relays are essentially the little brother of the contactor. So just like a contactor is nothing fancy, all it is a switch that is actuated electrically by a control circuit. A relay is also just a switch that is actuated electrically. It has a control side, and then it has the output side. And the thing that is unique about a relay compared to a contactor is, one, they're designed for low power systems, so that means they're less expensive, so we build our logic off of them. And also, you can build a lot of logic into these little relays. For instance, this voltage monitor. You can also have relays that will do things based on time. Let's say you have a well that should only be run for an hour every other hour. You can buy a time delay relay that allows you to open and close this switch every other hour. So during the first hour, no electricity is going to flow. During the second hour, electricity gets to flow. During the third hour, no electricity gets to flow. During the fourth hour, again, electricity gets to flow through here. And that's all because of this relay that we've installed into this control system. You can get to very complex systems on relays, but we don't need to get into all those details because we want to learn about the systems that we're running into.